let's go ahead and rejoin where we left off. So this was the slide we left off with the other day. So this was the big key. Inversely proportional to the stability of a carbocation in the same position as the leaving group. In other words, the more substituted the active carbon was, the slower an SN2 reaction is. Right, and we can see that, experimentally. These are all relative rates, which means they're unitless. We're just comparing one reaction rate to the next reaction rate. So the units or the numbers only make sense in context with each other. But if you have a secondary alkyl halide, call that our baseline for the reaction. A primary alkyl halide, whether it's a propyl group or an ethyl group attached that the bromine is attached to, they're between 10 and 100 times faster than any secondary reaction. And a methyl bromide is going to react 1,000 times faster than a secondary active carbon. And on the flip side, a tertiary active carbon reacts in a way that's too slow to measure. Basically, so we can't say that it doesn't happen, but we can say that it happens at a rate that it's not worth measuring. So it's effectively like saying it doesn't react. The reason we phrase it this way is just because we know that everything that can happen does happen, but it doesn't always happen in a rate that's measurable. So, and that really doesn't, and this is just with chloride as our nucleophile. Chloride is not a particularly strong nucleophile, but it turns out it doesn't really matter how good a nucleophile you have. We see the same reaction pattern for SN2. So if we're just looking at this reaction, we would expect this reaction to not happen at room temperature.
Why?
Because the active carbon, the one that has the bromine attached, has 3 carbons attached to it, and they just spatially, there's not enough room for a nucleophile to come in here and attack. Because having 3 carbons around that active carbon makes it really hard to sort of thread that needle and get your nucleophile to attach to that carbon. The problem is they actually tested this and they actually measured that it occurs quite quickly, but with a different rate law. So the reaction happens, we still get a substitution reaction happening, but now our rate is first order, not second order. So second order reaction, we said was concerted, right?
And second order is SN2, right?
Correct. The 2 stands for second order. So we said it was concerted. You needed your nucleophile to come in and attach at the same time that your leaving group is leaving. So you had to, so the concentration of both your nucleophile and your haloalkane both affected the rate, because they had to run into each other for that to happen. Our reaction changed in this case. If it's first order, let's try and write out a mechanism that makes sense. So if it was second order, this basically is the mechanism. It's a little bit more complicated because there's a proton transfer step, but I'll start by writing out the mechanism for this reaction as a SN2. And then we'll try doing it for the first order reaction. So if it was gonna happen. We had water acting as our nucleophile. And in a first order reaction. We're gonna have our nucleophile attack. But we can't have a carbon with 5 bonds. So our leaving group has to leave at the same time. And in this case, because we have water acting as our nucleophile. Oh, yeah, stood too close. Because we had water acting as our nucleophile, we actually get an intermediate as well, so. So it goes through that umbrella flip, which doesn't really matter because it's not a chiral carbon. Our leaving group has left. And now we don't just have OH attached here, though, we have H2O attached. What is the charge on that oxygen? Or does it have one?
Technically speaking, it's happy, but because it's electronegative, would it be positive?
Not because it's electronegative, it's because when it's neutral, it has 2 bonds and 2 lone pairs. So it's sharing more than it normally does. It's happy in that the valence is full.
Yeah.
So you're right, though, it is positively charged. So that if our final product is actually the alcohol, what is our next step in this mechanism going to look like? What type of step do you think it might be?
Does the OH, does the bromine come back in? Or does it stay bye-bye?
It plays a role.
Does it stay bye-bye? Oh, well, the bromine's negative and the oxygen's positive, so the oxygen goes with the bromine to go neutral?
That would make sense, but then you're forcing 2 electronegative elements to form a bond together,
So,
which doesn't really make sense. So I'll give you a hint, it's one of your 4 primary types of
yeah,
mechanism steps.
that might have notes, not in these notes. Oh. No. I don't think I have any of these notes. Wait, can we go over those ones again? Please.
So what are our 4?
Nucleophilic attack.
Nucleophilic attack. What did the bromide do in the first step? Leaving group leaves,
One transfer.
proton transfer,
Rearrange.
and rearrangement. So the oxygen has a positive charge, but it's more electronegative. So what part of the molecule would the bromide actually be attracted to then? That might make things more stable. It's already got a negative charge. It's not going to come into the lone pair. If the bromide snags the hydrogen from the oxygen, now the oxygen can be stable. So it's just a proton transfer step. So with these mechanisms, it takes a lot of practice. But one of the things you can always keep in mind is if you know where you're going, it's easier to get there. So if you remember what the product is,
The H to the O.
It's not from the H, it's from those electrons. You have to show where those electrons are going. So when the bromide grabs the H plus is not gonna bring the electrons with it because the oxygen is more electronegative.
OH doesn't leave to be an alcohol, it just says bye to one H and then
Correct.
it's attached as an alcohol.
Bingo.
Okay.
If it left as an alcohol, so
It's not an alcohol.
it's not an alcohol, it's a hydroxide. It's exactly what I was gonna say.
I know, cause I did that last time too.
Alright, so what I mean by if you know where you're going, it's easier to get there. If you know what the product is, sometimes it's easier to see what you need to do. So our intermediate looked like and then the rest of the CH3s. If you know you're trying to get from here to there, the only difference is you're missing an H plus. So if you keep your product in mind when you're writing these, a lot of times that'll help you from going off into some random side reaction that may or may not actually happen. It's a little bit like when you first learned how to drive and you didn't know where anything was.
Yeah.
And you got lost a lot, right?
It-
As you start to drive, you start to build up a mental map. Whether it not consciously, subconsciously, you have a better idea of where you are spatially in a town, right? Mechanisms work the same way. If you can know where you're going, the better you know your reactions, the easier the mechanisms will be. So with that in mind, so this was a two-step reaction. One step was the SN2 step, and then we just did a proton transfer to get rid of that extra positive charge. What is it gonna look like if it's first order? If it's stepwise? Think about what were the two steps that happened at the same time in the concerted reaction. And then separate them out.
It's the same as what we just did.
Almost identical.
Yeah, but so the bromine's gonna leave first and
Bingo.
our transition is gonna be. Because they can't happen at the same time in stepwise, but you have to make space before you can.
We can't have the nucleophile attack first because then we'd get a carbon with 5 bonds.
So then SN1 is always stepwise and SN2 is always the other one?
Exactly. That's the definition of those two. They're both gonna give you the same net result usually. But do you get there all at once or do you get there in 2 steps?
Stepwise is 2 steps, conservative.
Yeah, I'm gonna stop saying 2 because SN2 and SN1. So the 2 is for second order. SN1 is stepwise. And SN2 is concerted.
So first we're gonna have the bromine, the water, and the positive carbon.
Yeah, your first step is just bromide leaves and it's a leaving group. So all of your leaving groups are more electronegative than carbon.
Yes.
I was just pausing to see if I could make that absolute statement, and I think I can. There might be a case where you have a carbon as a leaving group, but there are special things happening there, so we'll get there.
I'm trying to.
Almost always, your leaving group is gonna bring the electrons with it.
Which would make the carbon positive.
Correct, so then we
Not-
have, which is not normal, and it doesn't like that. Because how many bonds does the carbon have now? It only has 3 and no lone pairs.
It's so.
So sad, because it doesn't have a complete valence.
The water's floating.
The bromide is now just floating around on its own. And the water is floating around on its own.
So how, like, this would happen so quickly though. Because
Yes,
the carbon is not gonna be very stable.
exactly. So that's exactly why the first step in this process is called the rate determining step, because the leaving group leaving is the slow step. Because you're going uphill in energy. This is why we talked about those potential energy surfaces, right? We just went uphill in energy to get here. So that's gonna have a large activation energy. And then as soon as that happens, this is no longer stable.
And so the oxygen.
So the oxygen comes in and attaches, and now we get the same intermediate that we had last time. Where we've got. We get that water attached. So you think that's a protonated alcohol. It's an alcohol that you've stuck an extra H plus to.
Yes. And then would we continue again to,
We don't usually end a reaction when we have a positive charge on our carbon-based molecule. So we would usually do, this is the end of the SN1 reaction, and then we just have a quick proton transfer to make it, to get our final product.
But isn't our bromide still just floating around?
It is. So that's a really convenient thing to come by and grab an H plus.
leaving, and then nuclear group? So it's leaving group, nucleophilic attack, and then it'd be a proton transfer.
Yeah. So you don't always have proton transfers on SN1 reactions or on SN2 reactions, but they're sort of like an afterthought. The SN1 got us here to a protonated alcohol, but we never stop there because that's not a stable molecule. So it'll always do that blast step.
But like technically the SN1 reaction ends.
Once you get to this blue structure.
Does it matter if you draw the arrow going from hydrogen to bromine or bromine to hydrogen? Eventually or right now?
Right now.
Okay.
Why? What do the arrows show?
Well, they're showing where the electrons transfer to, right?
And does the hydrogen have any electrons moving with it?
Oh, no, it's attached to the oxygen, so the bromine has to be the one that grabs
The
it.
bromine, and you'll notice that I drew the arrow coming from the negative charge on the bromine. A more correct way to do it would actually be to draw all 4 lone pairs on the bromide and show one of the lone pairs grabbing it.
Okay.
But if we know that anything with a negative charge has a lone pair, we can just, the shorthand is to show that the negative charge is grabbing it.
Got it. How you doing, Tom? Getting there, all right.
Okay, this is what we're doing for the rest of today, is practice with these.
I kind of like them.
They make sense. The problem is the volume of them. So the lowest score I ever got on a chemistry test was not this specifically, it was the second test after mechanisms were introduced, because I thought, oh, these mechanisms, they all make sense. I don't need to study that much. And I went in and realized that when I had a blank piece of paper in front of me, they actually still were really hard to get to the right endpoint.
Yeah.
So we're gonna add them gradually. Next quarter, you'll have tests where 30–40% of your test is mechanisms.
Yeah.
And that's tricky, because you'll have 10 to study from.
But do you always give us like the whole equation first and then say, okay, how did I get there? Or
We'll
you-
take those training wheels away eventually
and
for a
just,
few of the
will you
reactions.
ever give us just a beginning? Like, do we have to know what the end is?
So typically, generally that's 2 different reactions or 2 different types of question. The reaction questions, I would just say, here's your methyl bromide. And it reacts with water, what's the product? And those, and I'll just leave it blank and you have to fill in the product. So I call that that's a reaction question. What is the product? You don't have to show the steps to get there. And then the mechanism questions, I'll say, here's the reactants, here's the product, draw all the steps. And so it's really, this is, I generally give like 10 of these because they're faster. And they're 4 points apiece. And for the mechanisms, I'll give you a whole blank page, tell you what the product is, and they're worth 10 points apiece. And so there'll be 3, maybe 4 of them on a test. So different types of questions. The reaction ones you should have down almost like flashcards, like they're, you know, once you get the hang of these functional groups, they go quick. The mechanism ones where you have to stop and show, because we'll get to points where we do addition reactions. Addition reactions are a class where there's a lot of vocab associated with what type of addition it is. And so you know, when you have it down like, oh, this reaction is an anti-Markovnikov hydration, which is a lot of words to say, I know exactly what the product is really quickly. But drawing the mechanism for an anti-Markovnikov hydration might be 6 steps.
Do those words get added to the big long name?
To the big, no.
Okay.
It's talking about the type of reaction. Markovnikov versus anti-Markovnikov has to do with where you add the next one, but we'll get there next quarter. That's a next quarter problem.
It's just so interesting.
We'll talk a little bit about Markovnikov because it's one of my favorite scientists are human too stories is Markovnikov and a guy we're going to learn about next called Zaitsev. When we do elimination reactions, Markovnikov and Zaitsev were in the same research group together. They were both grad students together. And Markovnikov famously shut down Zaitsev's PhD defense. He like totally torpedoed him in front of the entire committee that was judging whether or not he earned a PhD or not. And started this whole back and forth that has a long story that goes along with it.
Did he beat him up?
I don't, well, he did intellectually. Zaitsev turned around and he waited for Markovnikov to publish the first of what was supposed to be 3 papers in a row. He watched him do it and he published the first one, and Zaitsev said, "You did that wrong."
That's pretty good. That's good.
And made him print a retraction and everything and totally ruined his whole plan for his whole career. Yeah, scientists can be petty too sometimes. But anyway.
Sorry.
No, it's okay. How are you feeling, Taylor?
Good.
Okay.
Got it. Okay.
All right, so based on that mechanism we just drew, try and draw a potential energy surface, the peaks and valleys. What is that going to look like for the reaction?
Well, we know that we're doing the stepwise one, right?
For the stepwise one, yeah.
We know that the leaving group leaving is gonna be our highest peak. And then it'll go back down, but then it'll go up again when the oxygen comes in.
So we have our leaving group leaving. So this is our intermediate state, right? That's when we have our carbocation. So uphill in energy. And then we got our oxygen with a positive charge on it. Is that going to be more stable or less stable than what we started with?
Is it more stable because the charge is not present?
It's more stable than this.
Yeah.
Because the charge isn't on the carbon.
But it's still not very stable.
It's still not as stable probably as what we started with.
Yeah.
So there's one more transition state to get to our final answer. our final product. So for every step, for every arrow that you draw in a mechanism, you have one transition state.
So. The first one's the leaving, right?
First one is leaving group leaves.
Okay. Yeah.
I don't have any eye drop, I might have some eye drops actually.
Do it on free.
Okay.
I don't want to keep extra contacts with me. You okay? Yeah.
I had that issue yesterday.
It's gone.
Got it, okay.
Got it. There they are. Can leave it out.
Okay.
So then the second one is just the carbon being positive?
So remember the transition states, the peaks are when something changes.
So it's the oxygen then for the second
For
one?
the second one, that's when the oxygen attacks the carbon. So one, leaving group leaves. Transition state 2 was our nucleophile attack.
And the third one is the proton transfer?
And 3 is that last proton transfer. Which won't always be there for these, right? Proton transfer as needed, you could say.
And these are the peaks?
Mm-hmm. Cause that's when you have energy.
So the peaks are these mechanism steps, which you can think of them as being the arrows, the reaction arrows that we draw. So going from step 1 to our reactants to the first intermediate has a transition state. Going from our first intermediate to our second intermediate has a transition state.
Why do you have an arrow in between your 1 and 2 and nothing happening?
Because I was saying that that was our intermediate, I was gonna label that and then I forgot. And I went a different direction.
Can we talk about the intermediate?
Is this our saddle?
So the saddle points are 1, 2, and 3, the transition states, because the side, just remember that these are not it's not actually a two-dimensional surface. We're drawing it just like going through a mountain pass. It's not a two-dimensional surface. If you took a cross section of it, you could visualize it as a two-dimensional surface. So these are the saddle points because if we
And the saddle's facing us, right?
basically the part that's going up and down would become,
Towards us.
and it would actually be even. If you want to try and, you can't visualize this, but I'll say it anyway. This is an n-dimensional surface, not a 3-dimensional surface.
Oh, it's like for.
N-dimensional meaning where n is the number of atoms that you have. Because every atom you have in a reaction could move and cause its own potential energy surface. So we're looking at a 2-dimensional surface, but it extends into 20 dimensions. But we don't care about 19 of those 20 dimensions. We're looking at just one cross section.
But it would take more energy to go into those other sections, right?
Correct. So all of those other 19 dimensions are all curved upward.
Yeah.
So
Cause it's like water, it's gonna take the path of the least resistance.
exactly, it's gonna go the lowest energy pass between the two states. It might bounce back and forth a little bit. Like if you think of a marble rolling back and forth at the bottom of a bowl, it doesn't actually sit all the way at the bottom of the bowl, right? It kind of can come up the sides a little bit. You might see a little bit of that, but it's not gonna go way up to the other sides. Unless you're going a totally different pathway and gonna make different products. That's like competing reactions. Competing reactions are you have two different ways you can go. They don't have the same energy to get there. They don't have the same elevation change. But they might both get you to the same point, or they might take you in two different directions. So it's. We literally don't have the firmware in our brains to be able to process what a 20-dimensional surface looks like. So the best we can do is a topographical map where you can kind of conceptualize what it is, even though we can't really picture it. All right, so, and you asked about the intermediates.
Yeah. What are those?
So the
Like-
intermediates are what we draw at the either end of an arrow. So this is our first transition state, is going from your bromide being attached to your bromine is left. The transition state is in between those two, right? Your intermediate is what you get after that step is complete. So your intermediate is
The positive.
It's positive. It's concave up, it's the bottom, a valley. But it's not necessarily as stable as what we started with. So we went uphill in energy through a pass to get to something that's still higher in energy, but it is still a somewhat stable state. It's not a transition state where we're in the middle of breaking bonds.
Is there a symbol for neutral that we have positive and negative?
Not really.
So an intermediate is what you get after the arrow, but before the next transition.
Bingo.
And
It's intermediate. It's in between two other things.
how would we know, maybe this is above what we're doing right now, but you know, when we were talking like the end versus the beginning, which one's higher to know what the reaction would be, how would we determine that?
Little bit is intuition. Meaning that you'll get more and more practice with it, but in this case. Because we wind up with the bromide leaving and the oxygen attaching, in general, bromine is a better leaving group than oxygen is.
So it's gonna be lower at the end.
So if bromine is the better leaving group, then at the end, we're gonna favor the product. Because we made something that is more stable, and we know that because bromide is the better leaving group than oxygen.
So electronegativity.
Electronegativity and those pKa tables.
Yeah, okay.
And so, how do we know? This is exactly what we need to worry, things we need to worry about with SN1 reactions. How good of a leaving group do you have? How stable is your carbocation? How good is your nucleophile? So how strong of an attacking force do you have? And then finally, we will have to talk about rearrangements now. But before we do that, I realized there was two other points I was going to make on this one. What do the reaction rates look like for SN1 with respect to the active carbon? So remember, the first slide we did today was we said, okay, the more substituted a carbon is, the slower SN2 is. What is that going to look like for SN1 reactions? If it's more substituted, is that going to make the reaction faster or slower for SN1? Why?
There's more to do.
There's more stuff in the way. But what's this? The slow step here is not,
It's the bromine leaving.
is the bromide leaving. So it turns out how substituted the reaction is, or the active carbon is, doesn't affect the leaving. I guess it does affect it, but not in terms of sterics. Because what do we know about carbocations? We had to make a carbocation intermediate right here, right? What type of carbocations are most stable? They're always going to be positive, but as far as how many carbons are around it, how did we rank carbocation stability?
Tertiary is more stable.
Tertiary is more stable than secondary, which is more stable than primary. which is more stable than methyl. So basically our reactivities for SN1 go the exact opposite of SN2. Because the more substituted the carbon was for SN2, the slower it went, because you had more stuff in the way, right? But for SN1, the more substituted it is, the more stable this intermediate. So if this is a tertiary group, for a secondary group, it might look like this, and then kind of merge back in. Because our intermediate is less stable, the intermediate that's a result of our rate determining step, because the intermediate is less stable, that step happens slower. So for SN1, tertiary is faster than secondary, is faster than primary, is faster than methyl.
Is that how we normally rate it?
Well, you just have this.
No, don't you
just have to
normally do
flip
it
the-
like that?
You just had to flip the triangles, the piranhas.
Isn't that how we normally rate it?
Yeah,
I thought it was opposite.
it's opposite for SN2.
Oh.
So SN1 and SN2 give us the same product, but they do it in opposite ways because one's concerted and one is stepwise. SN2 is concerted, which means we're more worried about the sterics, how surrounded it is by other stuff. SN1 is stepwise, which means we're more worried about how stable is this intermediate, which follows this trend. So the last question here, how do these reactivities compare to SN2 reactions? It's inverse, they're opposite.
The methyl isn't more stable than primary. More stable than secondary. Like it's not that opposite.
No, it's the speed, the rate of these reactions is opposite. The methyl is faster than primary, which is faster than secondary. So we're not talking about stability of carbocations. Stability of carbocations does not change. It's always this order. So we could say that the reaction rates for SN1 mirror the stability of carbocations. And the reactivity of SN2 is inverse to the stability of the carbocations. Right? So basically backwards.
Yeah.
So how do we know how fast an SN1 reaction is going to be? It depends on how good your leaving group is. It depends on how stable your intermediate is. How stable is the carbocation that you're going to make? Does the strength of the nucleophile really affect this? What is going to affect the rate of this reaction
For SN2.
for SN1?
The rate limiting, isn't that what happens after the first intermediate?
So because the first step has the highest transition state, the first step dictates everything about rate. Everything else is so fast after the first step, only the first step matters for rates.
So it doesn't affect the like high and low, like the highest and the lowest, but it's gonna affect the middle.
And it'll affect the equilibrium constant at the end. Because a stronger nucleophile, so all that matters for the rate is how high is this first step. And that first step does not involve the nucleophile at all. But what affects equilibrium constant is this distance. And a really strong nucleophile is gonna drive this down. So your equilibrium constant, how spontaneous the reaction is, how good your yield is at the end, is gonna be dependent on your nucleophile strength. But your rate is not affected by the nucleophile strength at all for an SN1 reaction. For SN2 reactions, it absolutely matters. This is one of the other things that the other big differences that we have to keep in mind.
Because the SN2, it all happens at once, so it's gonna affect that first one, right?
Exactly. Because the SN2 is concerted, nucleophile strength does make a difference. Alright, so we've talked about everything up to here.
Yeah.
The last thing we have to, so for all of these, predicting the products is pretty straightforward. You pull your halide off, you stick your nucleophile on in the same spot. Whether it's SN1 or SN2. However, SN1 adds one more wrinkle.
Why?
Because it goes through that carbocation intermediate. So there are advantages to SN1 though. For one, what does the geometry of this carbocation look like? What shape is it?
The bent,
It's not gonna be bent because you can see you have atoms attached to all three of them. It was tetrahedral until your leaving group left.
oh, what's 3? Tetra's 4.
Trigonal planar. It only has three things taking up space because there's no lone pair.
So it's just,
So it's trigonal planar, so they're all, it's flat and they're all 120 degrees from each other. Which means we don't need to worry about stereochemistry as much. Because, go ahead.
but when the oxygen comes in, it's gonna push things around.
It is, it'll go back to being tetrahedral. But your oxygen could attack from either side. If it's trigonal planar, it can attack from top or from bottom, right?
It's the same.
And it'll be the same. And so if you make something that has an R versus an S, if it goes through an SN1, you get both of them. You don't get just one stereoisomer, you get both of them because exactly. It was easier to make it through an SN1 mechanism, not an SN2 mechanism, and they got better yields, so they did that. So that's one less thing to think about for SN1. You don't need to worry about stereochemistry because you lose all that stereochemistry in the middle. As soon as it goes trigonal planar, then it doesn't matter if it started R or S because you went through something that's totally flat now.
And then since they're all the same, so you get both, right?
Mm-hmm.
Is there gonna be like where you're gonna want us to determine the direction that we end up drawing? Or are you gonna want us to draw both? Like,
So we'll get to that, but basically what you can do is if you're not favoring a single stereoisomer, the abbreviation we would just usually say is you get R plus S.
okay,
You get both of them in roughly equal amounts. In
So
this case, it
that's
doesn't,
one less thing to name now.
so that's one less thing to name, so
but only in S.
only for SN1, for SN2, we still have to remember it. So basically, this is a deep dive in there, here's a relatively, I'll be careful how I say this. This reaction doesn't have a lot of steps. neither of them, right? Neither of
Right.
these mechanisms have a lot of steps, but there's a lot of variables we have to consider. So this is basically a deep dive into a simple reaction that has lots of variables so that we can look at what are all the different pieces and how do they interact. And what if you get this down really well, all the mechanisms we add next quarter are gonna make a lot more sense. That's why we're taking our time with this. This is SN1, SN2, and then we're gonna add elimination has an E1 and an E2 for the same reasons. That's all we're adding between now and the final. Is this,
Okay,
right? So
so we're gonna get really good.
we're gonna get really good at this, and I'm even gonna give you a cheat sheet to study from when we get closer to it, once we had introduced more of these variables. So the last thing we have to worry about is rearrangement.
Yeah.
And rearrangement happens if you make it carbocation intermediate that could be more stable. So what does that look like? Let's say we started with this molecule. We've got a good leaving group. We've got a little stereochemistry. What is the intermediate going to look like when the bromide leaves? What's the first step of the reaction and what's the first intermediate?
It's just gonna be the ring with the one methyl.
Correct. Bromine leaves. And you get a carbocation on a secondary carbon. There's a hydrogen on the other side, right? Well, a secondary carbocation is not as stable as a tertiary carbocation, right? Is there a tertiary carbon next to the carbocation? That's a tertiary carbon, right? So it would be more stable to put the positive charge there. Basically, what happens is your carbocation has an unhybridized p orbital because it's got an empty spot in its valence, right? That's not all that stable. If you have a carbon next to it that has a hydrogen, that carbon hydrogen bond can sort of donate a little bit of electron density over to kind of make it more stable. That's why more substituted carbocations are more stable. The more carbons you have around it, the more those carbon bonds can give a little bit of electron density, so it's not completely empty spot. Well, but if this carbon is actually tertiary, what happens is these electrons get dragged all the way over. And they bring, I made this kind of messy, sorry.
That's okay.
It basically drags the hydrogen with it.
And then they're like kind of the same.
And now all of a sudden, what's the result after you do that rearrangement step?
Well, it's gonna be tertiary instead of secondary. Right?
Correct. So if we move the hydrogen over, now the empty spot is on the tertiary carbon instead. And now it's not tetrahedral anymore either. Because we dragged that hydrogen over, the carbocation that was secondary, that was planar, is now tetrahedral again. And so it looks kind of like the charge jumped over, but it's really, we left a gap when the hydrogen moved over.
So now that carbon that is tertiary does not have its last valence full.
Correct. Just like the secondary carbon didn't a second ago. But it's more stable than it was. The tertiary carbocation is more stable than the secondary carbocation. Which is what drives this rearrangement step.
So then when we get the nucleophile coming in, it's gonna come in from a different spot.
And it's gonna attack the tertiary carbon, not the secondary carbon. So if this reaction, if we said, I don't know, plus hydroxide as our nucleophile, if it goes SN2, you wind up with your,
It's gonna replace where the bromine was.
it's gonna replace what the bromine was, and you do need to worry about stereochemistry, right? So if it goes SN2, methyl stays where it was, the OH is down. So we went from cis to, exactly, so we went from cis to trans. If it goes SN1, we still pulled the bromide off and replaced it with a OH group, but it rearranged in the middle. So that's, rearrangements are tricky. They're also gonna be really fairly uncommon because it only happens when your leaving group is adjacent to a more substituted carbon. And we're gonna find out that in general, SN2, the only time that SN1 is really favored over SN2 is when is actually when your leaving group is already on a tertiary carbon. Is otherwise, for the most part, SN2 is a dominant reaction.
So if it was already like the last one, but if the bromine was there instead and then it came off.
Then it's gonna go SN1 every time, but it's already tertiary in that case, so you don't see rearrangement. So rearrangement, it's pretty rare. For the most part, unless I pick very carefully, where I say something like, draw the SN2 product and the SN1 product is something that I do on the final. Where I'll say, okay, we know SN2 is favored for this reaction, but show me that you understand rearrangements and show me the SN1 product also, even though it's gonna be very minor. But this is also why we never get any product in organic chemistry, no product is ever totally pure. Because even if 99.9% of the time it goes this route, you're still gonna get some amount of this as well, because that's just how probability works.
But then that's when you do like the filtering.
That's why we do the
That's
filter
when you
or
do it.
the recrystallization. Because if you get 99.9% here and 0.1% here. Well, if you add enough solvent to dissolve all of this, you definitely added enough solvent to dissolve all of that. And when you recrystallize it out, this will stay dissolved in the solution and this won't. You'll lose a little bit of this, but you'll lose almost all of this. Right, so that's why we do the recrystallizations, that's why it's such a common step, is all of these other competing reactions that are minor products, we basically want to remove all the minor products. All right, let's take our break there, and we'll come back and we'll do practice with SN1.
Okay.
So let's come back at 5 after.
No, I'm just almost tutoring until 8, so it'll work out fine, no matter what. Right.
Like they share all the same, like, kind of line.
We're doing this new thing in equity. Instead of the iPad, there's a QR code. And you like have an account and you go to like click all these buttons. Takes so much longer. I don't
It
know.
doesn't work.
I don't like QR codes in general or things that direct me through my phone. I don't have a very old phone. It doesn't handle all these new authentication apps very well.
I know.
So does mine, and she tried to check me in for the flight coming home the other day, because I had never used American Airlines when we went through Expedia. I'm like, I don't know what to do.
And it took forever.
It took
Things were not-
forever.
So it was like, I was in row. Like. E, like the very first one after first class. And she was like row 27 because of how long it took.
20, just 20.
It's yeah, make your opinions known because everybody's of the opinion that Gen Z really likes apps and wants more apps to do stuff with.
I don't
I want
want
less
that many
apps.
apps on my phone.
Yes. Every time I'm like, oh, we're gonna get this new app for group chat. I'm like, I have 5 group chat apps.
Right, we don't
I
need that,
need one.
right,
Choose one.
all right. Let's do some practice with this. So this is set up more like the reaction questions would be. Where it's, you don't have to show the steps. It might be to your advantage to show the steps in some cases, just to remind yourself how things go. But if you can do it all mentally, that's fine. So for this first one, if it goes through an SN1, what are we gonna get as our product?
It goes through S and G. So more steps.
More steps. So it can be helpful also to show what the intermediate looks like. So your intermediate, again, you wouldn't need to get full credit for this question. If it just says, what's the product? You don't need to show the arrows. But your first step is gonna be leaving group leaves for SN1. So then we get an intermediate that looks like this.
Plus chlorine floating around.
Plus chloride floating around.
Plus the OH.
And we still have the OH as well.
Which is a hydroxide group. not-
Bingo. It's not an alcohol till it's attached to a carbon.
Okay. So then the OH has a one negative
Correct.
on the H.
Not necessarily. That's just the way that it's traditionally written, but it's actually the oxygen that has the negative charge.
Okay. So the oxygen goes to where the fluorine does.
Do we need to worry about any rearrangements with this one?
I mean, like, because you asked, yes.
Well, but it's all the same, it's uniform.
They're all secondary carbons, right? So if it rearranges, you're still gonna have a secondary carbocation.
Nothing's really gonna change.
So in that case, no. We need to think about it, cause you always wanna think about it with SN1. When you draw the intermediate, think, is there a rearrangement that can happen to make things more stable? The answer is no in this case. So our
Except
final.
for that oxygen thing.
So that's, we wouldn't consider that a rearrangement, that's a nucleophile attack.
But it makes it more stable.
It does make it more stable. Rearrangement very specifically means within the same molecule.
That's your CL floating around.
Plus Cl floating around.
Was the OH going straight up or coming towards us?
Doesn't matter.
Good question. Even better question. So it is a chiral carbon still. But we went through this intermediate that was planar. So we're not gonna get just one of these stereoisomers, we're gonna get both of them. So you can either write that as,
Cause the OH could be straight, or it could be into the board, or it could be out of the board.
so because you can only make, there's only two mirror images. You can only have two possibilities. If you draw it straight, you're really just not showing which version of this it is. You're saying it's either of them, basically.
So we should just draw it straight.
In this case, so really what you made is you made both of these. But because we're gonna make them in roughly equal amounts, you can just draw it like this, as long as you tell me you understand there's still some achiral center. So you just have to write R plus S, or both enantiomers. Just so that you've seen it. I don't typically write it like this, but it does show up in textbooks. If you write one of the enantiomers, you can write plus En as shorthand for the other enantiomer. I've seen it more often like this, where it's just then labeled R plus S. Both of those are saying the same thing. Like I said, I typically use this version. But if you see it in a textbook, the top version is saying the same thing. So and this is all you would need to write to get full credit on the test. For this, it says, what is the product? Boom, that's all you need.
Not
All the rest of this is to convert, what's that?
Not even the plus floating.
We get lazy with balancing our reactions in organic chemistry. We care about the organic compound more. So technically, to be most accurate, yes, you would have the plus chloride in there as well.
Okay. Not marked down either way though.
I would probably look at how I wrote the question, if it said all products, or if it said major product, or if it like, there's a little bit of context involved in there. To be safe, yes, you would include that.
Second one.
Second one. What is our intermediate going to look like?
Bromine.
So our first intermediate and same thing, we always put the charge at the end of these polyatomic ions, even though it's really the nitrogen that has the negative charge. All right, we made a carbocation intermediate. Do we need to worry about rearrangement?
Cause it has a tertiary carbon next to it.
This has a tertiary carbon next to it. We only need to worry about rearrangements one carbon away. You'll never see a rearrangement jump 2 carbons. But we do have a hydrogen here that can transfer over.
So that's not our end friend.
Correct. We're never gonna end a reaction with a carbocation. Because almost always something is around, I think I can say always for this class, there's something around that will donate a pair of electrons to it.
Was that like a second intermediate?
Exactly.
Cause we still have. Floating.
We still have both of our ions still floating around, right?
So then the nitrogen comes in.
Then the nitrogen comes in.
And now that carbon comes back out towards us. Or is it both?
It's planar right now, right? It's flat, which means that's also valid.
What's also valid?
Both of these arrows, you can attack from the top or from behind.
So should we draw it all straight, just lines, and then say R plus S?
Did we make something that has stereochemistry? If we made something that had a stereo center, then yes, we'd be able to draw it all flat and say R plus S. But even though we started with something that had very specific stereochemistry, that's not a chiral center anymore. Because
Oh, who is the carbon, not the nitrogen?
both directions around this ring are the same. So that's our final product in red. We don't even have to say R plus S. All right. So let's talk about how we can estimate how strong different nucleophiles are. We've been just using pKa. We haven't really talked a whole lot about it. This is really going to come into play when we start talking about competing mechanisms. Because if you have a really strong nucleophile around, it's going to be less likely to go through SN1. Because a strong nucleophile is more likely to sort of seek out and find that partial positive and kick the leaving group off. So the stronger your nucleophile, the more likely it is to go through SN2 instead of SN1. And so our strong nucleophiles are basically anything with a negative charge is a reasonably strong nucleophile. And because if it has a negative charge, it's got electrons. In fact, it has extra electrons. And you can have something that's a good leaving group that's also a decent nucleophile. We'll talk about how solvent affects things because it turns out we can adjust how strong a nucleophile these halides are depending on what our solvent is. Our solvent affects that, which is weird because solvent's not part of the reaction, right? But it is part of the reaction conditions. You'll notice that fluoride is not on there because fluoride can be a weak nucleophile or a strong nucleophile. So let's talk about solvent a little bit. If you're in a non-polar solvent, SN2 reactions are pretty slow. Why might that be the case?
There's like not a lot of positive, like if it's not polar, it's all neutral.
And if it's non-polar, can you actually dissolve any of those? They're not going to dissolve in it, right? So and what about SN1 reactions? SN1 reactions are going to be even slower in a non-polar solvent, right? Because you have to make a polar intermediate, a charged intermediate, even worse than polar. So neither of these reactions happens very well in non-polar solvents. But in some cases, if we use a polar solvent, we can dissolve our strong nucleophiles better. But if our strong nucleophile also happens to be a weak base, we don't actually have much fluoride around when we do this in water. Because if you put fluoride in water, you actually make hydrofluoric acid for the most part. It'll mostly stay in this state. In which case and then we have a different nucleophile that's actually going to react.
Right. But don't we have like fluorinated water?
Fluoridated is a little bit different. Means you've added fluoride to it, which means you have small amounts of this in your water.
So it's slightly acidic when you drink fluoride.
Most water is actually slightly acidic, turns out, because if you dissolve CO2 in it, that actually makes it acidic as well.
So adding the fluoride doesn't help your teeth at all, just.
It does, the fluoride's not there to neutralize the acidity. The fluoride is there because your teeth, the enamel on your teeth is made of calcium fluoride.
If the water is still acidic, then it's just gonna break down your teeth.
Remember that acidity is a pH scale. And actually, if you add fluoride to your water, you actually make it less acidic. Because you take any acid that's around and you protonate the fluoride. You're adding a weak base when you fluoridate. And it's not really the acidity that you're trying to help with the fluoridation. Right. You're trying to, if you have more fluoride in your diet, your teeth stay strong longer, regardless of the acidity or alkalinity of the water. Okay. Right, so putting fluoride or any of these other strong nucleophiles in water is also gonna cause a problem. Because our strong nucleophiles are mostly pretty decent bases as well. So anything that's a strong nucleophile, we can't really use water as the solvent. Because then we're gonna get a whole mess of products, because we have all these competing reactions happening at the same time. If you put cyanide in water, you make hydrocyanic acid and OH. And then your OH can go on and be the nucleophile instead of the cyanide that you wanted to be the nucleophile. So we want solvents that are polar, but that can't act as an acid. So we call those polar aprotic solvents. Polar aprotic. Aprotic solvents means that they don't have H pluses to give up. They can't act as a weak acid. Right, so what does this look like? What are the other things that can happen if we do this in water? Well, if we have water as our solvent, we're gonna stabilize all of our ionic compounds, right? That's why they dissolve. And in doing so, we're gonna stabilize our nucleophiles as well. Even if we don't have something acting as an acid, if you have a polar solvent, you're gonna stabilize your reactants.
So it was a polar approach.
Aprotic. A from the Greek meaning without. And so we see this in we see this a lot when we look at SN2 reactions, or sorry, SN1 reactions, because our intermediate has a charge, right? We need a polar solvent for it to go SN1, because otherwise we're making an intermediate that is really unstable. The more polar your solvent, the more likely you are for SN1 to happen, because you've stabilized both your leaving group and your carbocation intermediate.
So the more polar solvent, the more likely you are to have an SN1 reaction.
Correct. So here's the net result of that. We want to stabilize our reactants and our transition states by using a polar solvent, but we don't want to stabilize them too much, or else they're going to stay stable the way they are, or we have other side reactions happening. So that's why we start using polar aprotic solvents. And so if we use a polar solvent, so this is for an SN2 reaction now, because it's concerted, it's one step. If we stabilize our reactants too much, that makes our reaction go too slow. We want them stable, but not too stable. Because look at the difference between the red and the blue lines here as far as the activation energy. The activation energy for the blue line is huge compared to the red line, right? So stable, but not too stable. And that's where the polar aprotic solvents come in. And so here's some examples of solvents. Protic solvents are anything where you've got a hydrogen directly attached to something electronegative. Anything where you can give up an H plus easily. Totally non-polar solvents or any hydrocarbon is a non-polar solvent, so. Benzene, hexane. Anything like that. The middle ground is what we want for the most part. Polar aprotic solvents. Like acetone. DMSO. Dimethyl sulfoxide looks a lot like acetone, except you replace the carbon with a sulfur in the middle. Acetonitrile, dimethylformamide. These structures don't matter that much, as so much as you understand, especially these ones. As long as you know that they're polar aprotic solvents. All right, so the polar aprotic solvents can stabilize. They stabilize our, especially positive charges, better than they stabilize the negative charges. And because they're aprotic, that means that you don't wind up with side reactions happening.
So it's mainly the ones with the double bond to oxygen. So why is the one with the P, the hexamethyl phosphoramide?
Nice.
not? Thank you.
Why is it, so it's just not as commonly used. It is a polar aprotic solvent. It's just not as these are the three most common polar aprotic solvents. Even acetone, we have acetone in the lab, we use it all the time, but acetone usually has small amounts of water in it. And also has other side reactions that can happen. So DMSO and DMF are the most common ones. And a lot of times you'll just see this written as hydroxide plus. You'll just see it written as above the reaction arrow if it's trying to indicate what the solvent is. It's just anything you see written above or below the reaction arrow generally means what is the reaction conditions. So the reaction has to happen in DMSO, but it's not a reactant. So we see that anytime we have a catalyst, we see it written the same way. Because it's basically saying, don't try to balance it with this, but it's important for the reaction. So we can look at a table of relative rates again. You'll see bromide is first thing when you see these tables of relative rates, usually what you want to do is you want to find where the 1 is, because that's going to be your baseline reaction. And then look at what's changing above and below that. So obviously we're changing our nucleophile here. And then we also have multiple columns. Here's our reaction rate in methanol versus in DMF. If we do this reaction in methanol, that's our baseline reaction. If we switch to DMF, it's 21,000 times faster.
But then, and like none of them are 1 anymore, but then the iodine is our lowest, right?
So iodine is still faster than it was, but it's slower than the rest of these. So, and that's because fluoride is actually a better nucleophile than the rest of these, but it's also the one that's most stabilized by a protic solvent. So basically the bigger they are, the worse they are as a nucleophile. But the less they're stabilized by a protic solvent. So iodine and bromide are better in a protic solvent. Fluoride and chloride are better in an aprotic solvent. But this number right there is significant, not like you have to write down those numbers specifically, but it's 82 million times faster fluoride reacting as a nucleophile is 82 million times better as a nucleophile if you do it in DMF compared to methanol.
That's just because of what it's going to attach to.
And because of how stabilized it is by the water molecules, by the methanol molecules. You put fluoride in methanol, it's gonna get surrounded by these partial positives that are gonna stabilize it and make it stable, and they're too good at stabilizing it. We don't want our nucleophile to be that stable. Because if it's super stable the way it is, why would it react?
Yeah.
And fluorides, because fluoride is roughly the same size as an oxygen, we see the most stabilization from these protic solvents. Iodide is just not stabilized that much in the same way. It is stabilized by a protic solvent, but not nearly as much because it's just so much bigger. And so even if you fit a whole bunch of methanols around an iodide, it's still a big ball of negative charge that can still come in and react as a nucleophile. Fluoride, though, can almost get completely obscured and surrounded by these methanols to the point where it can't react almost. All right, so what does this mean? The strongest base will also be the strongest nucleophile with one exception. You need both of these things to be true. If the reaction occurs in a protic solvent and your bases differ in size, so the bigger something is, the less the aprotic solvent matters. In general, stronger base means stronger nucleophile in an aprotic solvent. Basically, all that things we were just talking about only applies if we're comparing bases that are different in size and we're in a polar protic solvent. So again, this is a case of we're doing a deep dive into this very niche topic here. For the most part, solvent effects aren't going to matter. Solvent effects matter when you're talking about nucleophiles that are different in size and we're doing it in a protic solvent. If we're not doing it in a protic solvent, it doesn't matter. If we're in an aprotic solvent, strong base means stronger nucleophile. So most of the time, that's what we're going to be looking at. And we can also kind of get around this a little bit by using a protic polar solvent that is the conjugate base of the nucleophile.
Say that again.
I'll do you one better. I'll show you what I mean.
Okay.
If we put hydroxide as our nucleophile, with methyl chloride or chloromethane.
Yeah.
If we put this in a protic solvent that, like methanol, if we tried to do this in methanol, well, the hydroxide could actually wind up stealing a proton from a methanol and make methoxide. And so then we would actually have, this is our nucleophile. That's not going to give us the same product, right? But if we did this top reaction in water, if we just use water as our solvent, what do we get when hydroxide steals a hydrogen from water?
You mean the water would just turn into an OH?
Then the water just turns into the OH and the OH turns into a water. We get no net reaction basically, right? So in that case, it doesn't actually matter. We don't get any weird side reactions if we choose our solvent that matches the conjugate acid of our nucleophile. So if we wanted to use this as our nucleophile, if we wanted this reaction to happen, we could do it in methanol. Because then if our methoxide steals a hydrogen from methanol, we get another methoxide and another methanol back. We get no net reaction happening.
How are we gonna know in lab which one to choose? Like, are you gonna tell us there's OH in it?
I'm not gonna have you plan out your own reactions yet. So you don't need to worry about it in lab yet, because I've been doing all that for you. On the final for this class, no. The lab final for next class, yes.
That's great.
Less scary. You have time to think about this. It'll become more of the self-evident. All right. 10 minutes left. This is perfect.
And then we're doing lab, right?
That's right. We were gonna go finish up our lab. I'm gonna go get you started and then I have to run to the high school.
Great.
But yes. So we'll finish this and then be done, maybe a couple minutes early. If we have an SN2 mechanism. What is our product? And do we favor the reactants or the products at equilibrium? In other words, are we going downhill in energy? So for this first one,
I'm saying that's the charge. I thought it was like a plus sign and I was really, like, in the black.
yes,
In the black, I thought it was a plus sign, but it is the charge.
it's the
It was
charge.
just like the size of plus signs in the givens, I was a little.
Yes. It should be spaced out more. Well, oh, sorry, over here, that is just a plus sign. That's just a reactant plus sign. It doesn't have a positive charge until after it forms a fourth bond. Because nitrogen with 3 bonds is neutral.
You're supposed to remember what DMF is.
Yeah, just know that it's a polar aprotic solvent. You don't need to know the structure.
Okay.
So for this first one, which side is favored, products or reactants?
Yeah.
Why?
There's no charge. Everything's neutral.
But what's a better leaving group and what's a stronger nucleophile? Bromide, pK of -9. It's a much weaker base, which also means a much weaker nucleophile.
Which 3 is positive.
Exactly. So even though we made 2 things that are charged, the fact that bromide is such a good leaving group and such a a weak nucleophile compared to ammonia,
How did you figure that out from the chart again?
these numbers, remember, more negative on the pKa means a weaker nucleophile.
So then the. Yeah, makes sense why, not just because there's no charges, but also because of that.
Exactly. How about the second one? It's also a polar aprotic solvent, which means we can just use the pKa's. But first off, what's the product gonna be? So we went from cis to trans, trans to cis, thank you. And because the bromide is so much better of a leaving group than the fluoride, and we're in an aprotic solvent, we can just say that we're gonna favor the product side.
So this one, the fluorine is
So
not
we-
as good of a leaving group.
Which means it's a better nucleophile.
So we favored the reactants for the first one.
First one, we favored products as well.
Yeah, I'm confused.
Did I say it wrong in the first one?
Wait, no, so
So
we
we're
favored the
favoring the left
products.
side on both of these so far.
No.
Products is the right side.
Wait, but I thought for the first one we favored the other one because there were no charges and the
No, cause
bromide's a weaker leaving group, so we don't want it to be the leaving. Substitution.
No, it's a better leaving a group because it's a weaker nucleophile. It's a weaker base, means it's a better leaving group. If it's a weak base, that means it's not very good at pulling stuff towards itself, it means it's pretty stable on its own. So a weak base is also a good leaving group. So for both of these, we favor the products.
for the same reasons.
Same reasons.
So it would be fine to also say the products are favored for the second one because fluorine is a stronger nucleophile. Okay.
And we're gonna leave C alone for now. Cause we're out of time. And I want these top two are more important. So I'm not gonna confuse you with the solvent effects right now, because for the most part, that doesn't matter.
And for the first one, it's because bromine is a better leaving group.
That's fine.
Because bromine is a better leaving group, which is another way of saying that the nitrogen is a better nucleophile.